Hello everyone, good day. This is Helms Christian E. Pahoyo, a chemistry student from 2H1 section. Today we are going to talk about polarimeter, an analytical instrument. Polarimeter is used to measure the optical rotation of molecules in solution, or in other words, it measures the direction and extent of the polarization plane rotation. Depending on the type of instrument, the analyzer is rotated manually or automatically until the maximum intensity of the light falls on the detector. A few different types of polarimeters include Lorentz half-shade polarimeter, biquartz polarimeter, Lee-Peak polarimeter, manual polarimeter, and fully automatic polarimeter. In majority, polarimeter is composed of light source, polarizer, polarimeter tube, analyzer, and detector. So, what is an analyzer and how does a polarimeter work? Let us refer to our illustration to better understand this instrument. In our illustration, the process of measuring the optical rotation of molecules in solution starts with a light source. This is a monochromatic light that passes through the sample. A sodium lamp is usually used as the light source and the wavelength of its D line is 589.3 nanometer. Did you know? Light as it surrounds us is unpolarized. This means that each light wave oscillates randomly in one spatial direction. This unpolarized light will pass through first with a polarizing filter. This filter does not rotate, and this is where conversion of unpolarized light into polarized light takes place. We can affirm the converted unpolarized light by the double-headed arrows. From this multi-headed arrow that symbolizes random oscillation of light wave in one spatial direction, or unpolarized light that is converted into a polarized light whose light waves do not oscillate randomly. Afterwards, the polarized light will pass through an optically active substance to measure the angle of rotation. Optically active substances change the polarization direction of the light wave. These are the chiral substances which have molecular systems whose asymmetry results are in handedness. These chiral substances have a pair of non-superimposable mirror image shapes. Examples of optically active media are sugar, lactic acid, quartz, calcite, and sodium chlorate. Going back to our illustration, the optically active substance is contained in the polarimeter tube, and this causes the rotation of the plane of the polarized light. This polarized light will rotate either clockwise or anti-clockwise when it passes through chemical substances that are optically active. Notice that in our illustration, the plane of the vibrating light has changed after going through the polarimeter tube. Then, here comes the analyzer, a rotatable polarizer. It is rotated until no light goes through the second lens. The angle is then measured to determine the optical rotation of the optically active substance. The detector was positioned at the opposite end of a tube containing the optically active sample, and the user will use his or her eye to judge the alignment when least light was observed. The angle of rotation was then read from a simple fixed to the moving polarizer to within a degree or so. The amount of light rotating is known as angle of rotation. If the light rotates to the left or in an anti-clockwise manner, it is a level isomer, or its angle of rotation is levorotatory. And if it rotates to the right or in a clockwise manner, it is a dextro-isomer, or its angle rotation is dextro-rotatory. Why is this important? The angle of rotation allows you to ascertain the identity and quality of substances as well as their concentration in mixtures. It can also indicate the progress of reactions and conversions. Polarimeters are used in a wide range of applications, from the determination of the purity and concentration of ingredients in pharmaceuticals to the maturity testing of agricultural products like measurement of the sugar content in beverages and candies. That's all, and thank you for watching.